This is Mark, and here's my homework 7 video. I will show my room right now to show that I have no cheat sheet hidden somewhere. On my table, I have the formula sheet and the constant sheets. Here is the problem statement. Let's get it. So, right off the bat, we can draw a temperature time diagram with K in the y-axis and T the x-axis. We know it only stops at 2 points. One is at the boiling point, the other is at the melting point. Now the first stop, since we know it's a uniformly decreasing temperature, must be at the melting point. To list these 2 points, we can go into the function sheet and find the corresponding data, with Mercury's boiling point at 630 K and melting point at 234 K. So now we have this, we can set up the function. We know that Q equals to negative L times M, and for QB we have negative L vaporization times M. For QM have negative L heat of fusion times M. Thus the ratio between QB divided by QM would give us L vaporization divided by L fusion, because the mass cancels out. What this means is that vaporization goes (272 divided by 11.8). Now we know P equals to Q divided by T, since it's the energy over units, energy over time, which is power. And we know P itself equals to AE, emissivity constant, T4 minus 0 here, because we're in space and there's no backward radiation. We would have PB equals to AE constant, TB4, PM equals to AE constant, TM4. So PB divided by PM equals to TB4 divided by TM4. I will take a quick break and show you what I got here. For this part, this is what I used here. Find PB, PM, find a ratio between them. We don't have a lot of units to work with, so we better work with ratio. And over here is P equation given. P has its own P equals force power, and this will lead to here. TB and TM are what we found here. But, for the sake of simplicity, I'm gonna keep it as these two abstract numbers. And we know PB divided by PM is also QB divided by time B divided by QM divided by time M equals to TB4 TM4. Effectively, we get a 27.2 divided by 11.8 equals to TB4, TM4, TB, TM. Yep. And here's what we got. Continuing from here, just shifting variables around, we will know that T melting, which is the second time we're trying to find, equals to 630 times the force power divided by 234, the force power, times TB divided by 272, 11.8. TM. So here we have it. Knowing TB equals to 10 minutes. I will punch this into the calculator to find out the final answer. Yep, TM equals 22.8 minutes. Right here. But gotta be more precise also what we show. 22.8 minutes, the satellite will stay at a fixed distance. And what is a fixed distance? Well, we know intensity equals to power divided by 4 pi times distance squared. Then those two have equal intensity as the satellite needs to do that at all time. So PB 4 pi dB squared equals to PM 4 pi dm squared. Now, shifting stuff around, you'll be able to get PB PM equals to dB squared dm squared, since 4 pi cancels out. PB divided by PM is TB for TM4 equals dB squared dm squared. And a little bit taking square root on both sides. TB squared TM squared. Now we know that dB divided by TB squared times TM squared equals to dm. Here's the function we're going to use, and here's how I derived it. Pretty simple as that. Some simple mathematical operation based on this equation for intensity. Now just plug and chug. We know it's at 500 meters. So it's 500 times 234 squared divided by 630 squared equals dm. This will give us hopefully a nice number. in theory, it should be a number much lower than the first distance. Just because the temperature is lower, you need to get closer in order to have the same intensity of heat. It's dm equals to 68.9 meters. 6.9 meters. And there you have it. We now have found the distance and the time it's gonna stay for the satellites. It's gonna stay at 68.9 meters for 22.8 minutes. And that's it. Thank you for watching my video. See ya.